Hey everyone, welcome to this video. We're just doing some applications of logarithms. Make sure you have your guided notes. Right, there's not really any, well I guess they're not really guided notes, just practice problems. There's not really anything new to instruct. I'm just showing you how to go about solving some of these logarithm problems that involve real world applications. But you know how to do it all. I'm just kind of helping you walk through some of the steps. So let's look at this first one. It says you are cooking alicha, an Ethiopian stew. When you take it off the stove, its temperature is 212 degrees Fahrenheit. The room temperature is 70 degrees Fahrenheit. And the cooling rate of the stew is R equals 0.046. How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? Use Newton's law of cooling that states T equals T naught, or T sub 0, minus TR to the E minus RT power plus TR, where T naught is the starting temperature, TR is room temperature, R is the cooling rate of the substance, and T is time. So basically, it's just kind of plug in the numbers that you know and solve. Okay, so let's see here. We need T. So T is the temperature that we want it to become, which is 100 degrees. TR is room temperature, which is 70 degrees. T naught is the starting temperature of the substance, which is 212 degrees. R is the rate of cooling, which is 0.046. And we want to find little t, right, which is the time it takes for it to cool down to 100 degrees. So we just take these, plug it into our formula. So we have 100 equals 212 minus 70 to the E minus RT power, E minus R, which is 0.046 times T plus 70. Okay. First step we're going to want to do, right, we're solving, so reverse PEMDAS. We're going to do our add and subtracting. So we're going to subtract 70 from both sides. So 30 equals, and I'm also going to simplify inside real quick too. So 212 minus 70, that is 162. Oh, sorry, 162. 142 to the E minus 0.046 T power. All right, let me grab my calculator real quick. All right. So at this point, obviously we can't get 30 and 142 to be the same base, so we're going to have to use the, we're going to have to convert to the inverse to solve this. So base stays the same. So log base 142. What was outside is now inside, so of 30. And what was inside is now outside, E minus 0.046 T. I'm going to add E to both sides, or subtract E from both sides. So negative E plus log base 142 of 30 equals negative 0.046 T. Divide everything by negative 0.046. And this is equal to T. Okay, now we do all our steps first, and then we plug it into the calculator. Right? If we start plugging things in the calculator and don't do all the steps at the beginning, our decimal places will be off. And it could be so far off that even our whole numbers are off. All right, so let's check this out now. So just using the calculator, right? You can use Symbolab or your own calculator if you want. So let's see here. I got log base 142 of 30. So you should get 0.686 and then 3026781. I'm going to subtract E, so minus E. So now I have negative 2.03197915, and then divide by negative 0.046. I get T is approximately, because we're rounding, T is approximately 44 we'll say 2 minutes. Okay, now 0.2 minutes, you don't have to do this, but in case you're wondering, 0.2 minutes, let's see here. 120 over 10x. So 0.2 minutes is 12 seconds. So you can also say it is equivalent to 44 minutes and 12 seconds. Okay, but these are your answers. This one's probably a little easier to write, huh? Is this still going? Okay, I thought I accidentally clicked the pause button. And that's it for that one. Okay, I like this one because it kind of shows you why we blow on our food, right, to cool it down. If we let it cool down naturally, look, this would take forever, right? And in fact, this isn't completely a good model because 212 degrees Fahrenheit is the boiling point of water, not stew. Boiling point of stew would actually probably be more, be a lot higher, and so this would even take even longer, right? And that's why we blow our food off. It's because when we serve it, we tend to serve it a lot higher temperature than what we can eat, and that act of blowing our food, the steam off of our food, helps to cool it down faster, right? The rate increases a lot, so it cools it down faster. And then also there's less substance, right? So, like I said, not a perfect model, but I like it. All right, let's do the next one. This is very similar. So we're going to use the same formula, Newton's law of cooling. So it says you are driving on a hot day when your car overheats and stops running. The car overheats at 280 degrees Fahrenheit and can be driven again at 230 degrees Fahrenheit. When it's 80 degrees outside, the cooling rate of the car is R equals 0.0058. How long do you have to wait until you can continue driving? Right, so we want it to be 230 degrees. Right, because we want to drive our car again. We don't want to be stuck on the side of the road. The room temperature, or just the outside temperature, right? That's what room temperature is 80 degrees. The initial temperature of the engine we're starting with is 280 degrees. Okay, and that's when the car overheated. And our cooling rate is 0.0058, and we want to find the time in minutes that it takes for the car to cool down so we can drive it again. All right, so once again, we have T equals, so we have 230 equals 280 minus 80, 80 to the E minus 0.0058 T plus 80. Okay, using that same formula that we used in the first question. Subtract 80 from both sides, I get 150. Now 280 minus 80 is 200 to the E minus 0.0058 T power. We're going to do our conversion. We're going to convert to a logarithm. So base stays the same. Log base 200 of 150 is equal to E minus 0.0058 T minus E from both sides. So negative E plus log of 200, or log base 200 of 150 is equal to negative 0.0058 T. Divide everything by negative 0.0058, and that's what we get for T. So we're going to plug that in our calculator. So let's see, we have log base 200 of 150, get 0.94570311256, keeps going on for forever. Subtract E, so minus E. That gives us negative 1.772578703 for forever, right? And then divided by negative 0.0058. So T is approximately 305.6 minutes, which is, let's see, that's 6 hours, 5 minutes, and 0.6 is 36 seconds. That is a long, it's not 6 hours, sorry, 5 hours. 5 hours, 5 minutes, 36 seconds. That is a long time to be waiting on the side of the road for your car to cool down. Okay, that's why I like this one and made this one, is because it's really important, right, while you're driving, to be checking your gauges, right? Don't just check your speedometer, right, to know how fast you're going. If you're worried about a lead foot, that's the reason you got cruise control, right? Another really important thing to be checking is the other gauges off to the left-hand side. I guess this way for you. Off to the left-hand, no, it'd be this way for you still. Off to the left-hand side of your speedometer, right? Check your battery level, right? It tells you the battery level, if it's charged or if it's losing a charge. If your battery's not working, you can't start your car, right? That's bad. Check your oil temp levels, okay? And then check your engine temp levels, right? If your engine overheats, that's how long it's going to take for it to cool down. Right now, obviously, it's a little bit different in real life. This is a very basic model, right? As the sun goes down, as things get cooler, the rate of cooling goes up, so it cools down a little faster. But I mean, even if it takes away an hour, which is the rate would have to go up a lot for that, you're still waiting for 4 hours, right? So it's always good just to be aware of things and check things and just be have them pending in your mind, than having that problem occur, right? So don't just look at your speedometer. Don't just look at your RPM, right? Check your other little gauges over there. They're there for a reason. Okay. Let's move on to the next one. Sorry, I have my papers right here. Okay, this one's really fun. Okay. So number 3, when X-rays are fixed, when X-rays of a fixed wavelength strike a material X centimeters thick, so X is how thick the material is. The intensity I of X, so that's our function, that's intensity, of the X-rays transmitted through the material is given by I of X. I'll write this here. I of X is equal to I naught, which is the initial intensity of the X-ray, times e to the negative mu. Mu is a specific value depending on the material, and I give it to you in the question, times x, right? Remember, x is how thick the material is. And then the table shows the values for mu for various materials and X-rays of medium length. Okay. So part A. We want to find the thickness of aluminum shielding that reduces the intensity of X-rays to 30% of their initial intensity. Right, so the initial intensity is I naught. We want it to be 30% of that. Now remember, 30%, if we convert that to a decimal, is 0.3. So I want I of X to equal 0.3 I naught. Okay, 30% of the original. So I'm going to start plugging some stuff in. Instead of I of X, I'm going to put 0.3 I naught is equal to I naught times e to the minus mu. Now, part A says for aluminum, so it gives us mu. Mu is 0.43 times x. Now we're going to solve for x. I'm going to divide everything by I naught. So I get 0.3 is equal to e to the negative 0.43x. Convert to our logarithm to get x out of the exponent. So base e is natural log, so natural log of 0.3 is equal to negative 0.43x. And then divide everything by negative 0.43, and that is equal to x. If I put that in my calculator and approximate it, we have a natural log of 0.3 divided by negative 0.43, and we got about 2.8 centimeters. 2.8 centimeters is a little over an inch thick. Okay. I'm going to write that over here. So aluminum on the periodic table of elements is Al, I believe, right? Well, we'll put it there anyways. Al, 2.8 centimeters. All right, now let's go on to part B. I'm going to erase some stuff, but we're using the same formula because it says Do the same thing. In part B, it says repeat part A for copper shielding. So let's see here. I'm going to remove, I'll just remove from here. Okay, so once again, we have 0.3 I naught is equal to I naught times E. And now for copper shielding, mu is 3.2. So negative 3.2x. Once again, divide everything by I naught. So 0.3 is equal to e to the negative 3.2x. Convert to a logarithm. Natural log of 0.3 is equal to negative 3.2x. Divide everything by negative 3.2, and that gives us x. Put it in your calculator. Natural log of 0.3 divided by negative 3.2. And we get x is approximately 0.38, we'll say 0.4 centimeters thick. Okay. So copper is Cu. And so that's, we'll say 0.4 centimeters. Okay, and then part C says we need to do it for lead. Oh, where's that? So let's see, we have part C now. So 0.3 I naught is equal to I naught times E to the negative. Now, mu for lead says 43, so negative 43x. Divide everything by I naught. 0.3 is equal to e to the negative 43x. Convert, so natural log of 0.3 is equal to negative 43x. Divide by negative 43, and that's what x equals. So x is approximately, let's put that in our calculator, natural log of 0.3 divided by negative 43, 0.03 centimeters. Okay, and I always get iron and lead mixed up. Pretty sure iron is Fe, so that means lead is Pb. So lead on the periodic table, you don't need to know this, I'm just labeling for part 4, right, so we don't forget things. Lead is 0.03 centimeters thick. Okay, now part D. Okay, so part D says, and this is the cool part, your dentist uses a lead apron on you before taking x-rays for your teeth to protect you from harmful radiation, right? Because when you go to the dentist or even the hospital or whatnot, they take an x-ray of your face, they put that lead shielding around you, right? And it is lead, that's why it's kind of heavy, because lead's a very heavy metal. Heavy metal. Not to be confused with like Metallica, right? Anyways, sorry, I lost my train of thought. Oh, it's very heavy, right? So it kind of feels heavy. But there's a reason why they use lead. And it asks you, based on parts A, B, and C, why would you use lead? I'm going to give you a second to pause the video. Okay, now I'm back. The reason they use lead, look at how thick these metals are. If we were to use aluminum, that shield that you put on yourself at the dentist's office to protect from the X-ray radiation, like in your important organs, would have to be over 1 inch thick of aluminum. Now, and it's not like it's hollow aluminum. It's literally 1 inch thick of pure aluminum. Right? It's not hollow. That's crazy, right? And even copper shielding is 0.4 centimeters, right? Which is a little less than 1/2 inch thick. That's still 1/2 inch is still a lot. If you look at anything, 1/2 inch is still a lot, right? Your Chromebook, right, is less than 1/2 inch thick. And then look at lead. Lead is 0.03 centimeters. Okay, so 2.58 centimeters is 1 inch. 0.03 centimeters? Let's see. What would they even be? That is 3/100ths of a centimeter. So that is that many centimeters. And we want that to equal some number over how many, that's an inch, that's centimeters and inches, right? That's like 0.06 inches, which is 6/100ths of an inch, which is 3/50ths of an inch. That's something that you don't even measure with a tape measure, right? It's crazy thin, right? And that's why they use lead, is because they use less material. It's cheaper to make, and lead's already a pretty cheap metal, right? Aluminum is not cheap at all, and copper isn't. I don't think it is anymore. At least copper isn't very cheap. It never really has. When I was growing up, it wasn't cheap at all, right? You could get a lot of money for recycling copper, especially like wires and things like that, recycling, and aluminum, right? Like aluminum cans, things like that. You get a lot of money for recycling. But lead is pretty cheap, right? Lead is very abundant, and you use very little of it, right? Lead 3/50th of an inch. So it's cheap. It's really thin. You use barely any material, right? And it acts just as well as aluminum that's over an inch thick. And that's why they use lead when protecting you from radiation. There's other reasons too, but this is a nice little fun way of, and kind of a basic reason of why. Okay, let's go on to number 4. The apparent magnitude of a star is a measure of the brightness of the star as it appears to observers on Earth. The apparent magnitude M of the dimmest star can be seen with the telescope is M equals 5 times common log of D plus 2, where D is the diameter in millimeters of the telescope's objective lens, and M is the apparent magnitude, how bright the star appears to us. What is the diameter of an objective lens of a telescope that can reveal stars with magnitude of 12? So basically, we want to plug in 12 for M and get D by itself. So 12 is equal to 5 times common log of D plus 2. Subtract 2 from both sides, we get 10 is equal to 5 common log of D. Divide by 5 both sides, 2 is equal to common log of D. Okay, we want D outside of the logarithm, so we need to convert. So base stays the same. The base of a common log is 10. Okay, 10 squared is equal to D, so 100 millimeters is equal to D. And that's your answer. Okay, part 5. Black pen is running out. You can see it's kind of smudging. So part 5, an investment that earns a rate of return R, so R is a rate of return, so basically interest rate, doubles in value in T years, where T is equal to the natural log of 2 over natural log of 1 plus R. And R is expressed as a decimal, right? Whenever you see rate, like percentages and mathematical formulas, they're always expressed in decimals. Okay, we don't even use percentages in math ever. It's always a decimal or a fraction. The only reason we actually teach you how to use percentages is because everyone else, like all the non-math people, uses percentages, right? And sometimes they use them in statistics. But even in statistics, I've never used percentages. I've only ever used decimals and fractions, right? So whenever you see a percentage, okay, if you're in doubt, always convert it to a decimal. What rates of return will double the value of an investment in less than 10 years? Okay, so we want to know where T is less than 10. So if we plug in 10 and get an answer, We just know it's all the answers that we know it's all the answers above that. Okay, because we're looking for R, we're looking for a rate. So if the rate is lower, if we get less interest, it would take longer to make money, right? Because you're getting less interest. But if the rate is higher, it takes less time. So because we want less than, all the rates that are higher than what the answer we get will be true. All right, so let's look at this. We're going to plug in 10 for t. So 10 is equal to the natural log of 2 over natural log of 1 plus r. So I want to get r by itself. So here I'm dividing. I need to multiply everything by natural log of 1 plus r. So I get 10 times the natural log of 1 plus r is equal to natural log of 2. Divide by 10, so natural log of 1 plus r is equal to natural log of 2 over 10. Now, when we divide by 10, it's the same as multiply by 1/10, right? So the natural log of 1 plus r is equal to 1 over 10 times the natural log of 2. When we multiply outside, it's the same as exponent inside. So natural log of 1 plus r is equal to the natural log of 2 to the negative, or excuse me, not 2 to the negative, 2 to the 1/10 power. Ooh, look here. We have a logarithm on both sides of the equal sign, which same function. The bases are the same, right? Both base e, natural log. So what's inside has to be equal. So 1 plus r is equal to 2 to the 1/10 power. Subtract 1 from both sides. R is equal to 2 to the 1/10 power minus 1. So r is approximately, let me put that in my calculator real quick. 2, where is that at? To the 1/10 power minus 1 is approximately 0.07. We're on 0.07. So any rate where r is greater than, and it has to be strictly greater than 0.07, will give us will double our money in 10 years. All right. If you want that as a fraction, it's 7 over 100. If you want that as a percentage, right? So an interest rate, it is 7%. Okay, remember percentages are out of 100. So if you want a percentage, you move the decimal place to the right twice because 100 has 2 zeros. So 1, 2, 7%. Okay. All right. Number 6. Oh, I forgot to number these ones. These were on different These were on different documents when I printed them out. I just forgot to number them. Okay. In a research experiment, the population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 1,218 flies, and after 3 days, there are 4,252 flies. How many flies will there be after 5 days? Round your answer to the nearest whole number. Use the formula P equals P naught times e to the RT power. This is usually, I call this the PERT formula. It's continuous growth. So first thing we need to do, we need to figure out R. Let's plug in some of the stuff we know. So we know, well, let's see here. Actually, first, P is the ending population, the end population. P naught was the initial population. We don't know that. Didn't give it to us. R is the rate of growth. And T is the time in days. Okay. So let's see. After 2 days, there are 1,218 flies. So we have 1,218 is equal to P naught. We do not know the initial population of the flies. times e to the r. We don't know rate. It hasn't given us rate either. But we do know the time. It says after 2 days. Right? So 2r. Now we can't solve this because we have two variables. So we can't solve it. But we do have some more information. Right? It says after 3 days, there's 4,252. So 4,252 flies is equal to P naught times e to the 3r. Right? T is 3. Okay. We now have a system of equations. Okay, remember that from SM1, a system of equations? What I'm going to do is I'm going to get P naught by itself. And then when I get it by itself, what it's equal to is I'm going to plug it into here. Because they're the same. They're equal. Right? So actually I'm going to do it here first. I'm going to do it to this one. So to get P naught by itself, I divide everything by e to the 2r power. So 1218 divided by e to the 2r power is equal to P naught. Now because P naught is this, instead of writing P naught here, I'm going to take this and plug it in for P naught there. I just realized that P naught just really sounds like peanut a lot. Maybe next time I'll use a different letter. So 4252 is equal to 1,218 divided by e to the 2r times e to the 3r. Okay, now let's simplify. E to the 2r, or e to the 3r divided by e to the 2r. Well, when we divide exponents and the base is the same, we subtract. So we're doing 3r minus 2r, which is just 1r. So this is 4,252 is equal to 1,218 times e to the 1r power. Divide by 1,218. So we get 4252 over 1218 is equal to e to the r power. Convert it to a logarithm. So natural log of 4252 over 1218 is equal to r. Okay, so we know r now. Now I'm not going to use a decimal yet, right? Because if I simplify, if I use a decimal, I'll get a different answer. So this is the natural log of 4252 over 1218. Okay. Now I need to find the initial population. Okay, because in the end, we want to find the end population after 5 days. But I also need the initial population in my formula. Well, hey, look, I got a formula for it right here, right? P naught is equal to 12,018 over, or 12,000, my goodness, 1,218 over e to the 2r power. Well, I know what r is, so P naught is equal to 1,218 over e times 2, or to the 2 times natural log of 4252 over 1218 power. Okay, that's my P naught. And let's figure that one out. So let's see here. We have e to the 2 times natural log of 4252 divided by 1218, oops, 1218. Okay, and then we have 1218 divided by that answer that we just got, which is 99.943, and it says round to the nearest whole number, right, in our question. So P naught, rounded to the nearest whole number, is 100. So we started with 100 flies. Oops. And now we know enough information to find out how many flies are left over after 5 days. So what we're going to do is we're going to have P is equal to, we want to know what P is. P is equal to P naught, which is 100, times e to the r, which is natural log a 4252 over 1218 times 5, right, for 5 days. And we just put that in our calculator. So we have the natural log of 4252 divided by 1218 times 5, and that is in the exponent of e, and we want that to be times 100. So after 5 days, p is equal to 51847.7 flies, but we round up to 8. So 51,848 flies after 5 days. Woo! That's why there's so many fruit flies around, right? Because I don't know if this isn't an exact model, but yeah. All right, let's do the last one. Okay, so find the time required for a $500 investment to double at an annual interest rate of 3% compounded semi-annually. Semi-annually means twice, right? 2 times a year. Round your result to 2 decimal places. Use the formula A equals P times 1 plus R over N to the NT power. Okay, this is interest formula, right? It's very, very well known, very, very popular. And actually, the formula we just used, the PERT, comes from this one, right? It's as n approaches infinity. But we don't really have a whole lot of time this year to do that, so I didn't show you that. It's okay, I'm just giving you the formula. So A is the ending amount, P is the starting amount, N is the number of times the principal is compounded annually, R is interest rate in decimal format, and T is the time of years. We want to find T. So we know P is the original amount, which is 500, right? It says we invest $500. We want to double it. So we want it, A should be 1,000, right? What comes out should be 1,000. R, the interest rate, is 3%, which is 0.03. N is the number of times compounded annually. It's semi-annual, so 2 times. Right now, if it was monthly, it would be 12 times because there's 12 months a year. If it was weekly, it would be 52 times because there's 52 times in the year. If it's daily, now I know daily kind of changes because it depends, what if it's a leap year, blah, blah, blah. We just use 365, which is just the accepted amount that we tend to use, right, in it for a year. If we compounded it quarterly, right, well, how many quarters are in a dollar? In $1, 4. So quarterly is 4 times a year, right? Things like that. But anyways, this says semi-annually, so just twice. And then we want to know what T is. That's what we want to know. Or how long is it going to take? So I'll just take my numbers in and plug them in. So A is 1,000. P is 500. 1 plus R is 0.03 over N is 2. And then N is 2 again. And then times T. So first things first, reverse PEMDAS. I got to divide by 500. So 2 is equal to 1 plus 0.03 over 2 to the 2t. Now I do it in the parentheses. 0.03 divided by 2 is 0.015. Now 1 plus 0.015 is 1.015 times 2 to the t. Now I'm going to convert to my logarithm. So base stays the same. Log base 1.015 of 2 is equal to 2 times t. Divide everything by 2. So t is approximately, let's see here. Log base 1.015 of 2 divided by 2 is approximately 23.3 years. 23.3 years. And that's your answer. So if you're only getting 3% back on something, it'll take 23 years to double your money, right? So if you're only getting 3%, make sure you put in lots of money if you want to double, because it's going to take forever for it to double, right? All right, that's it for the video. Once again, if you need anything, send me an email. Coming after school. I'm available every day after school.